everyone. So for this video, we're going to finally dig into VSEPR theory, which stands for valence shell electron pair repulsion theory. So what this really means is that electrons take up space. Electrons are negatively charged, therefore they actually will repel each other. So let's look at an AB2 molecule. That means A is the central atom and it has two items or two atoms coming off of it, bound to it. So that would be this example here, right? Ignore the holes in the middle here. But what are we seeing? What kind of properties are we seeing with this? So the reason why it's linear is because these electrons want to be as far away from each other as possible. How can they maximize their distance between each other? If they were any closer, right? If we bent it, they would be, they would not be as far apart as possible. So what can we conclude about the AB2 structure? So we're going to conclude that it's linear, and we can conclude that the bond angle is 180 degrees. So that's the first thing that we can conclude about linear, right? So AB3 means that we have a central atom with three things coming off of it, right? That could be three atoms. That's what that would look like. So it's almost like having a pizza or something and you slice it into threes. So what this one is called is Trigonal Planar. Why is it planar? Because it's flat. So it's Trigonal Planar. Now, if any of these were to get as kind of angle up, they would get closer to the other one, right? They're maximizing their distance. So they're 180 degrees away from each other this way, which maximizes their distance. And then what are the angles here? 120. So it seems that this is called Trigonal Planar. And we have 120 degrees. Now, here is where we get a little bit tricky. Now, let's pretend that we have a structure that has, and I'm going to do this, maybe it has a lone pair and two bonds, right? A lone pair and two bonds. So we're going to come across structures like that sometimes. So when I play with these, I like to leave this here. I take the atom, but I leave this here to represent that there's still a lone pair here. Now, I always say that lone pairs, they take up more space. They have more repelling power, if you will, than bonded pairs. So what's going to actually happen is these are going to come together oh so slightly, right? So if they were all perfectly bonded and there was no polarity, nothing, it would be 100 degrees perfectly, right? If we were in this situation. But if I remove one of these, what happens? This is a lone pair. It's two electrons that do not have a nucleus over here, a positive nucleus. So these are basically like untamed, kind of. They take up more space. This is actually covered pretty thoroughly in the Chapter 9 slides. So what happens is that this has extra repelling force and requires a little bit more space. So these are consequentially kind of squeezed together a little bit more. So I'll never ask you for that, but it could also be, so if we could write it that way, right? So if we have two bond, one lone pair, what do we have? If the bond angle is less than 120. So this is if they're all bonded. So we have two options on this one. So I actually brought some markers so I could color code here. So there's two options for the AB, right? We could either have 120 if they're all bonded, or less than 120 degrees if we have two bonds and one lone pair. Why didn't I do that lone pair trick up here? Well, what happens if we have a lone pair like this, like a carbon monoxide? Two things can't have an angle, right? To have an angle, you have to have a central atom. And since there's no central atom here, that doesn't apply. So let's make this look nice. Yes. And then we're going to move on to what I hope we have enough room for is AB4. So that means that we have something with 4 electron densities, regions, right? That would be this. I'm going to clear these guys out. So this is the tetrahedral, and magically, if you notice, any way you put it, we have one sticking straight up. The bond angle here, if you notice, it's actually slightly bigger than a right angle. So it's actually 109.5. So I'm going to write all the way over here. So if they're all bonds, it's 109.5 degrees. And this is called tetrahedral. Tetrahedral, sorry for all this messy writing. This is the first time I've ever done this online, this lecture. So they're all bonds, it's a tetrahedral. So now we have this situation where you say, okay, Carla, what if we pop one of these off? Well, if you notice, it's not a trigonal planar, right? Because is that flat? No. And what happens with this lone pair? It's the same thing that happened with our trigonal planar. This lone pair is going to repel these. So it's actually going to push them in a little bit slightly. So the bond angle there will actually be 107. So if you have 3 bond, 1 lone pair, it's actually 107. By the way, all of this information is on the lab report, Lab 7, or I think I labeled it Lab 8. Lab 7. All of this information is on Lab 7. So then you have a situation where maybe we have, ooh, and it falls off. What if we have two lone pairs, right? So this is now, this has a new name. This is called, where you have 3 bonds, and when you have 3 bonds and 1 lone pair, this is actually called Trigonal Pyramidal. And it is a little pyramid when you set it down. It's a nice little pyramid. So this is actually called Trigonal Pyramidal. Yeah, it's actually called Trigonal Pyramidal. And just to go back, this situation with AB3, if we take away one of these, it's called trigonal planar if they're all bonded, but when we take one away, what would you call that shape? I'd call it bent. Sorry. Right. So that's a bent shape. These are the molecular shapes. So, now we come and we say, okay, we have a trigonal planar. It has a tetrahedral electron geometry. And if I take another one away, now what would you call that shape, right? I'd call it bent. Now, we not only have 1 lone pair that is repelling the bonds, we now have 2. So it's sort of like they gang up, and they repel each other. So it extra squeezes these together. So it's not the perfect 109.5, it is now 104.5. So if you have 2 bond and 2 lone pair, it is 104.5. And what would you call that? We call that bent as well. So let's go back, let's rewind, and let's differentiate between molecular shapes and electron geometry shapes. So we're going to do example number 12 from your homework, which is what is the OSO bond in SO2? The answer says the bond angle is slightly less than. So I can't guess if SO2 has lone pairs. I can't guess if SO2 has what shape it is. So what we're going to have to do is we're going to have to draw it. So SO2, S has, we're in this column, so we have 6 electrons, and 2 times oxygen, which also has 6, so I need 18 electrons. That's what I'm looking for. So S is in the middle, oxygen, oxygen. Complete the octets on the outside, guys. That's 16. So I need 2 extra ones right here. So it looks like, how many electron density regions are there? There are 1, 2, 3. So this is an AB3 molecule, right? With 2 bound, 1 unbound. We can build that. 2 bound, 1 unbound. So what's going to happen with this lone pair? It's going to push this in. So the answer is, if it was a perfect AB3 molecule, we would have 120 degrees. But since we're pushing it in just a little bit more, it's going to be slightly less than 120. So it's going to be less than 120 degrees. Let's go ahead and do number 6 from your homework. It says the electron and molecular geometry of SO3. So we're going to go over electron and molecular geometry right now, but let's go ahead and get SO3 out in the open. So again, S carries 6 and O carries 6. There are 3 of them. So it's 6 plus 18, so 24. So S bound to O, bound to O, bound to O. Complete the octets on the outsides. Now how many electrons do I have? 24. But the octet on the S is not satisfied. So what am I going to do? I'm going to get rid of one of these, and I'm going to make a double bond here. All right. So this is also an AB3 molecule. But in this case, we do have a double bond. But this double bond exists here and here as much as it exists here, so we just have this shape. Now, S does not have any lone pairs on it, correct? So it's an AB3, all 3 are bound. So what shape are the electrons in? Trigonal planar. What shape are the, what shape is the actual molecule in? Molecule means only pay attention to the atoms. Trigonal planar. So that's the answer for both, is it be a trigonal planar, trigonal planar. So let's do an example that is not specifically in, I believe it's on your lab. So let's do NH3. N has 5, H has 1, and there's 3 of them, so I need 8 electrons. So N to H to H to H, I have 6 electrons in my drawing now, so put 2 here. All right, so I have 8. So let's show that with our model. It's an AB4, correct? With 3 bonds and 1 unbond, 1 non-bonded, right? So that's what it looks like. What shape are the electrons in? The electrons are still in a tetrahedral shape, right? So the electron geometry is still tetrahedral. This is, the electrons are in a tetrahedral shape, AB4. But how about the molecule itself? Molecule means ignore lone pairs. So you could even, if you're trying to decipher the molecular shape, that is a classic trigonal pyramidal. Okay. So that is how we do electron and molecular geometry using the VSEPR theory for up to a coordination number of 4, which, 4 electron dense regions. I will go ahead and make one for A5 and 6, coming right up.